Hello everyone, I'll be talking about local and global root numbers of elliptic curves. These are the people involved in this project. I will start with elliptic curves, their reductions, local and global root numbers, densities, and local to global. We define an elliptic curve as this over field K as a solution of this Weierstrass equation. If you know that characteristics is not 2 and 3, with an admissible change of variables, we can reduce it to this form. We are looking at the reduction of these coefficients, and we want to know whether the reduced Weierstrass equation is still an elliptic curve or not. If we say that E has good reduction at P, if it has discriminant of valuation is 0. In this case, the reduced version is also an elliptic curve. If it's not the case and the valuation of C4 is 0, then it is a multiplicative reduction. And if the valuation is strictly bigger than 0, it has additive reduction. We use Tate's algorithm to determine these types. It takes as an input prime and the coefficients of Weierstrass equation and gives us the coefficients of the minimal equation as well as the reduction type, Kodaira symbol, and the conductor. The local root number is defined as the sign of a local functional equation of E modulo P, and it is plus or minus 1 depending on the reduction, but it is not easy task to determine it. And we define the global root number as the multiplication of local root numbers up to a factor negative. This comes because of the fact that infinity has a negative local root number. The L function attached to E is defined like this. And similar to Dyer conjecture says that the vanishing order at S equals 1 of the L function equal to the rank of E. Since we know that rational points of elliptic curves is a finitely generated abelian group, there is an algebraic group, and it actually says that analytic rank equals to algebraic rank. Assuming which similar to Dyer conjecture, we obtain this conjecture. It says that global root number is determined by the rank, and the question is, what is the proportion of elliptic curves with global root number plus or minus 1, or the percentage of elliptic curves with even or odd model Weyl rank? Yes, we can pass with conjecture. There is an important theorem proven by Bhargava, Skinner, and Young. It says that at least 16.5% of the elliptic curves have rank 0, and at least with 20.68% have rank 1. Using the conjecture, we get that at least 60.5% have global root number plus 1, and the other part has minus 1. So the question is, can we obtain or improve these proportions unconditionally? I will talk about local densities. Let's say we are given non-negative integers. These are the coefficients of coefficients of Weierstrass equation. We impose this valuation condition on it, and there is a translation group which took the coordinates to this, and we also denote the equality in this part like this. I mean, this means that valuation of V6 is strictly 1. And there is a subgroup of this translation group defined as in this form, and we provided this. We know that it has index P to the E plus F plus G in T. Now we use the usual periodic measure, and we have this. So given a subset, we want to look at its measure. We can think of it as the probability that a random Weierstrass equation lies in S. For example, if we have this means that A2, A3, A4, A6 coefficients have valuation greater than or equal to V2, V3, V4, V6, but we want the equality here. These all parts contribute to this, but since we want strict equality, we have this part because we cannot choose P here. Otherwise, we would go up, so we get this factor. And as a notation, we will use this. The action of T is measure preserving, and it leaves discriminant C4 and C6 invariant. If the discriminant is not 0, then it induces an isomorphism of elliptic curves, which is important for us. Given some property or type, we look at this set. We want to know the measure of this type along elliptic curves. And we define the local density as just the measure of this set, periodic measure. Now we focus only on the minimal Weierstrass equation, because for each isomorphism class we can represent it with minimal Weierstrass equation. And for non-minimal ones, we know the measure of this. It can be calculated, so we can pass through them. And if we also specify the type, we have this set, and looking at its measure, we get the local density. Its local density is defined as in this form. Actually, Tate's algorithm give a way to get the minimal Weierstrass equation. At each type, A is translated with some T, and if it lands in BT, then we say that A is minimal and of type T, and it is given with if and only if form. I mean, if I know that I can translate A to something in BT, then it's of type T, and Tate's algorithm gives the way of doing it. Hence, looking at the measure of this set, we get the density of minimal elliptic curves of type T, this part. And we also know the stabilizer of this set. To get the local density, we just multiply it by this index, because we have as many as this index, many representative of T's. So we just multiply by it and get the local density.
Okay, so this table is given by Cremona and Sadek. For each type T, it gives the measure of the base set and the index of the stabilizer, and their product will be the density of minimal Weierstrass equation with type T. Now we care about the type and the density of the type, because types determine root numbers. So a theorem by Connell, for p greater than or equal to 5, we have a way, knowing the type, to find root numbers. So the first 4 points hold for any prime p. The root number at infinity is -1, good reduction is 1, split multiplicative is -1, and non-split is 1. And for additive reductions for p greater than 5, we calculate the epsilon p symbol, and it gives us the root number. So for p greater than or equal to 5, it turned out that every reduction type determines uniquely the symbol epsilon p. So for every reduction type, we have a unique WP. So the densities will be the same as the densities in this table. Okay, now for p equal to and 3, we use the notation CIK for Ci over p power k. And when k is the valuation, we just write C prime I. So when p equal to and 3, we have the following tables. Given the Daira symbol and the valuations of C4, C6, and delta, we can find a condition. This condition it's equivalent to the root number being equal to 1. So the root number is 1 if and only if we have this condition. When we have no conditions, the root number is always -1 for those valuations, for example. What we did here, for every case, we calculated the density and then the relative density of this condition being satisfied. So, this is our table. Instead of having the condition in terms of valuations, we have them in terms of the base sets with those relative densities out of the type. So for type 2, they add up to 1. And those densities are the relative density of the row. So if we're here, half of those have root number 1 and half of those have root number -1. So, okay, that's for p equal to. and that's for p equals 3. So a demonstration how we reached those results. For example, for p equal 2 and type 2, we use Tate's algorithm. And then every minimal elliptic equation can be turned into this base set. After we translate the singularity into 0, p will divide the whole coefficients. And if p squared doesn't divide a6, then we're in type 2. So the valuation of a6 is exactly 1. That's the base set of type 2. So we have for type 2 6 cases according to that paper. So we need to find the valuation of delta, the proportions. So the valuation of delta could be found in terms of A31, for example. So we'll have a condition on A31 that will help us calculate the probabilities. Now, suppose we get how the probability split for each type, then this condition will give us the relative probability for each root number. For simple conditions, for example, C prime 4 congruent to 1 mod 4, it's equivalent to valuation of A4 equal 1. So that will be have relative probability half. However, for complicated conditions like, for example, C prime 6 congruent to 5 or 5 C prime 4 mod 8, we just go over all the cases of the AI mod 8, and we count those satisfying the condition. And that's the mathematical code. Okay, now with those local results, we go to global results by developing some local to global theorem. So on Z to the D, we define a density, the uniform density. For a set Z, the density of Z will be the limit as x tends to infinity of the number of points in Z with size less than x over the whole integers of size less than x. And then on Z, we can impose some local periodic conditions. So they will be a set S of prime numbers. And then for each prime, we have a subset UP of ZP of D. Those will be the conditions. And then our set Z will be the A in ZD, such that A belongs to UP for every P in S. So that means that we require A to satisfy all these P conditions. At every prime P, A is in UP. So if S is finite, then the uniform density of Z is exactly the product of the measure of UP, where mu is the periodic measure on ZP to the D, the product periodic measure. Now if S is infinite, we need an extra condition over those family. Namely, we need them to be admissible. So if I take Z to be the point satisfying UP, I impose some rank M. And if the limit as M tends to infinity of the density of those points satisfying UP for some P greater than M is 0, then we say that those family form an admissible family of conditions. So if we have an admissible family of condition, we can write it in the form of infinite product. So let UP be an admissible family of conditions. The measure of each UP is SP. Then we have that the summation of SP converges. And if we take a finite set of prime S, then the measure of A in ZD such that A satisfies UP if and only if P is in Z is the finite product P in S of SP and the infinite product of the others, 1 minus SP. So we have the product rule in terms of densities for admissible family of conditions. Okay, so an application for that, we say an elliptic curve is semi-stable if at every prime P the reduction type is either good or multiplicative. So the density of integral various equations, which are minimal models of semi-stable elliptic curve, is 1 over zeta of 2. So a scheme of the proof, we take UP to be the opposite of this condition, that is being not good nor multiplicative, having bad reduction type at every P, UP at this P. So the measure of UP is 1 over P squared. And this family could be proven to be admissible. So by applying the previous result, we get that for S equal phi, the family is product of this, which is 1 over zeta of 2. So now the future work, if we know the whole WPs and WE is obtained by those local conditions, how can we use the local to global results to say something about the density of elliptic curves with root numbers either 1 or -1? Okay, thank you.